This video is going to be about quadratics in standard form, which is y equals ax squared plus bx plus c. And the first section we're going to look at is how c affects the graph of the equation. So we have three different equations here. You might notice that they all kind of start the same. It's negative 2x squared plus 4x for all three of those. But that last number, that constant at the end, is different for for each of those three equations. So the first one, it's -3, then -1, then +1. And underneath it, it identifies that in this case, c is -3, c is -1, c is 1. Okay, so c is just the constant at the end of this standard form equation. And we want to see how that relates to the graph of each of these equations. So for our first one, there's this little bubble here because it's trying to draw our attention to this point right here, which is 0, -3. For that second one, okay, it's pointing to this point right here, which is 0, -1. And for the last one, we're looking at this point right here, which happens to be 0, 1. And hopefully you're recognizing that it's pointing to those points because those are the y-intercepts of those graphs, okay? So we can conclude that when we have an equation in standard form, a quadratic equation in standard form, that constant at the end, okay, that c, is going to be the y-intercept of the graph of y equals ax squared plus bx plus c. Okay, and it makes sense if you think about it, because hopefully you remember that y-intercepts happen when x is 0. Okay, and if we look at one of those equations, I took the first one. We have negative 2x squared plus 4x minus 3, and I ask you to find f of 0. Remember, when that number is on the inside of the parentheses, that's just telling you that x is 0. Let's plug 0 into the equation and see what happens. So we'd have negative 2 times 0 squared plus 4 times 0 minus 3. And what's really nice about this is we'll have to do 0 squared first, okay? But anything, that's just going to be 0. 4 times 0 is 0. And the only thing that's left is that constant at the end. So that's why in any of these standard form equations, that constant at the end is going to be the y-intercept, because when you plug in 0 to that equation, that's going to be the only thing that's remaining. Okay, so next we're going to move on to finding axis of symmetry in standard form. I'm going to just go back up here for a second and look at all three of these graphs. They all had that same axis of symmetry. That hasn't changed for all of those, which leads me to believe that the C does not affect the axis of symmetry. So let's talk about what will affect that axis of symmetry. Oops, sorry, too far. An axis of symmetry in standard form is x equals, okay, because axis of symmetry is that vertical line. So it's going to be x equals something. In this case, it's negative b over 2a. Okay, that's very important to know. You'll need to know that when you're dealing with a standard form equation, you need to know that the axis of symmetry is x equals negative b over 2a. So we have an equation. We have f of x, remember, just the same thing as y, that shouldn't throw you off at all, equals negative 2x squared plus 4x minus 3. Okay, and we are going to find the axis of symmetry. So remember, this negative 2 is our a, positive 4 is our b, negative 3 is our c, even though it doesn't matter right now. And we're going to use that x equals negative b over 2a. Okay, so our b is 4, so it's going to be negative 4. Keep in mind that if b in this case, well, in this case it's positive, but if b had been negative, it would be that negative, which means you would be writing a positive number here. But because we're plugging in a positive 4, it's negative 4 over 2 times a, which is negative 2. So this would be negative 4 over negative 4. And our axis of symmetry is x equals 1. Okay, and this actually was the first equation from our trio of equations above. And if we go back and look at our graph, yes, indeed, the axis of symmetry was x equals +1. Okay, so now we are going to go into graphing a quadratic in standard form. Okay, there's a couple steps. The first one is going to be to find and graph that axis of symmetry. Okay, so we're going to start with x equals -b over 2a. A is 2, b is 4, c is 3. So it's going to be x equals -b, which is -4, over 2 times 2. So -4 over 4. And our axis of symmetry is x equals -1. So I'm going to graph that first. We often use a vertical dashed line to represent our axis of symmetry because it's not technically part of our graph. It's not part of the parabola we're graphing, but we definitely do want to put it on there to help us graph this parabola. Next, we're going to find and graph the vertex. Now, hopefully you remember from when we did vertex form that the vertex is on the axis of symmetry, okay? So that means that we need a point somewhere on this vertical line, which means that the x coordinate of that point is going to be -1. So we're going to plug -1 in to that original equation and figure out what that corresponding y value is going to be. So I'm just going to rewrite my equation down here, 2x squared plus 4x plus 3. And I want to plug in x of -1 and evaluate it. Okay, order of operations. So exponent first, that'd be -1 squared is just 1. So 2 times 1 plus 4 times -1 plus 3. Multiplication is next. I'm going to do them at the same time. So that's 2, that's -4, and that's 3. And 5 minus 4 would be 1. So our vertex, okay, we knew the x from the axis of symmetry. So that's -1. We plugged it into that equation to find the y. Our vertex is at -1, 1. Okay, so we have our vertex. We can kind of tell what it's going to look like because that A still tells us, if it's going to be opening upwards or downwards. Okay, it is positive, so we are going to have a normal, rightly shaped U parabola as opposed to an upside down one. So we know that this is going to be the bottom point, okay, that minimum value, but we still need to find some other points to help us graph this parabola. Okay, the really nice thing about standard form, okay, is that we do quickly know what its y-intercept is. Okay, if our equation was 2x squared plus 4x plus 3, we just discovered on the first page that that c is the y-intercept. Okay, because when x is 0, that's going to give you the y-intercept. So our y-intercept in this case is 3. So that's another good point that we can plug into our graph. Okay, and then we can also reflect it across the axis of symmetry. So not just a 0, 3, but also -2, 3. Okay, and we're not going to have too many points with these, but we do want to put as many on as we possibly can. So I'm looking for probably at least one other point, which I can then reflect to the other side. Okay, we always want to stay near the axis of symmetry. So I can't always tell you like what are good points to plug in. Okay, you have to look at what's near it. So over here, okay, we already have 0 and -2. I'm thinking 1 or -3 would be a good point to plug in. And if I have a choice of those, I'm definitely going to plug in 1. To me, plugging in +1 is definitely a lot easier than plugging in -3. You could plug in -3 if you wanted to, but I think it's silly. Okay, so we're going to plug 1 into this equation. Okay, so once again, 2x squared plus 4x plus 3. Okay, the nice thing about plugging 1 in, and I'll show you in a second, okay, 1 squared is just 1. This is just 1. Okay, anything times 1 is itself. You can kind of just ignore the x's almost because you're just going to end up with ones there. So really it's just going to be 2 plus 4 plus 3, which is 9. So when x is 1, y is 9. So I have another point that I can plug into my graph. And if I have 1, 9, then that must mean negative 3, 9 is also going to be a point. Okay, and now there's clearly not going to be any other points that fit. They'd be way too high on my graph. So I'm going to attempt my best to draw a U shape and make sure I put some arrows at the end. Okay, I do want to point out that I could have also used that rate of change pattern that still does apply here. When we had done this, we had said that as the x increases by 1, the first one jumps up by 1, the next one would jump up by 3, then by 5, and so forth. So that's in that parent function, that's what's going to happen. But in this case, our a was 2, so that will affect how much each one jumps up. So our first one would jump up by 2, then by 6, and then by 10, and so forth. So if I look at my vertex, if I can go back up, okay. If I look at my vertex, okay, I want both of them there. Okay, here was my vertex. For as my x increases by 1, I want to count up 2 spaces. So you'll see here, over one value of x, I would jump up 2. And then from there, it would be 6 more. So as I move over one more value of x, 1, 2, 3, 4, 5, 6. Okay, so if you're not a fan of plugging in points, that rate of change pattern really does help. Except when the a is a fraction, sometimes that's not so fun, and plugging in points is probably your best option there. Okay, so let's try one more graph together. So this one here, I didn't list the steps, but we'll still go through them. I see that a is a decimal, so I'm thinking that rate of change pattern is not great here anyway. But we have to start with our axis of symmetry. So x equals negative b over 2a. B is 3, so negative 3. And 2 times negative 0.75. I'm thinking maybe it'd be nicer to say negative 3/4. Okay, so we could do 2 times negative 3/4 would really be negative 3/2. And now it's just a compound fraction. Negative 3 divided by negative 3/2 would just be negative 3 times negative 2/3. And our 3's reduce, and we're really just left with x equals negative 2. So our axis of symmetry is that x equals negative 2. I'm sorry, I totally just ignored the fact that it's a negative times a negative. So backing up, not x equals negative 2. Okay, our 3's reduced, but our negatives did not. Well, so we have negative times a negative is a positive 2. That looks better. So x is positive 2. Okay, now we need our vertex. So our vertex will be on that axis of symmetry. So we know its x value is 2. Let's plug 2 in to our equation. So I'm going to say g of 2, I'm just going to be fancy here, is negative 0.75 times 2 squared plus 3 times 2 minus 4. I'm going to change that to negative 3/4 because I think that's going to work out nicer again. So I did my exponent. Now I need to multiply here. We get negative 3 plus 6 minus 4, which is negative 1. So we have our vertex at 2, negative 1. Okay. Our A is negative, so it is going to be opening downwards. The next thing to check for is that Y-intercept. Okay, our C here is negative 4, which means our Y-intercept is negative 4. So that'd be here. and we can reflect it over to that side. Okay, and we need a couple other points. Now, they're not going to work out nicely, but we can still do our best and estimate here. I'm thinking let's plug in 1. If I have a choice of 1 versus 3, I like to plug in 1. So we have g of 1 is -3/4 times 1 squared plus 3 times 1 minus 4. Okay, remember it's kind of like you can ignore those 1s because it's just going to be itself. So 3 and -4 is -1. And with that, it's -1 3/4. So at 1, it's -1 3/4. I can reflect that over. We can plug in -1. Okay, let's see what happens there. Okay, I could do -1 or 5. It's the same thing, but I think 5 is getting a little big. But we have -3/4 times -1 squared plus 3 times -1 minus 4. So we're going to get -3/4 times 1 squared, which is just 1. This is going to be a -3 and a -4. So that would be -7 3/4, which would be 7 3/4 right about there. And I can reflect it over. I'm thinking that's probably all that's going to fit on my graph. So I'm going to connect it with my U. And we have our graph. So just to recap our steps, first you find the axis of symmetry by using x equals -b over 2a. Okay, graph that vertical line on your graph. Next, you plug in that x value to find its corresponding y value, and that gives you the vertex, which you will also put on your graph. From there, another great point to put on there is the y-intercept, which is just that c value. So you would put that on the y-axis and reflect it over the axis of symmetry. And then you need a couple other points, even if it's just one, which you end up reflecting. But you just choose some x values around that axis of symmetry, plug them in, and find that y value that goes along with it. Okay. Compare properties of quadratic functions. So we have a fountain, okay, and we have little fountains on the side of the big fountain, okay, and you can see that they are forming some nice looking parabolas. Okay, so we have fountain A and fountain B. It gives us an equation for fountain A, while it gives us a table of values for fountain B. And they want to know which trajectory reaches a greater height in feet. Okay, so these parabolas are opening downwards, okay, which means we are going to be looking at the vertex of each of those. And that y value of that vertex is going to be the greatest height of that fountain, okay, that maximum value. So I'm going to start with fountain B because to me that one's a little bit easier, okay. So at -6 it's 5, at -5 it's 8, at -4 it's 10, but then at -3 it jumps back down to 8 and then 5. If I'm thinking of this and knowing there's some axis of symmetry, okay, I know that this 10 must be that biggest value, okay, because as it's going, it's reaching 10, okay, and then it starts dropping back down again. So for fountain B, its greatest height is 10 feet, okay? We need to figure out now the greatest height of fountain A, okay? So we need the y value of the vertex. That's going to be the greatest height. Okay, but we can't know the y value until we know the x value. And the x value is going to come from the axis of symmetry. So we're going to do x equals -b over 2a. Okay, we have a, b, and c. So -b is -2. Okay, 2 times a, and there's an invisible number there. A is -1. So this would be -2 over -2. Which means our axis of symmetry is 1. And now we can plug that in to our equation. So -1 times 1 squared plus 2 times 1 plus 8. Really, it's just -1 plus 2 plus 8, which is 9. So for fountain A, its maximum height is going to be 9. For fountain B, we said the maximum height was 10. So fountain B is going to be the answer because it has a greater height in feet. Okay. And our last example, converting vertex form into standard form. Okay. Each of our forms gives us different information, and sometimes certain information is helpful, more helpful in a situation than others. But in case you need to convert back and forth, let's go over how to do that. So we have Mia tossing a ball to her dog. Okay, you can see that it is forming that parabola, even though they didn't draw the whole thing. They give us the equation for that parabola. And we are first asked to look at the vertex form that they gave us and describe what it tells us about that situation. Okay, so hopefully remember that in vertex form, our vertex is HK. And in this case, the H is 2 and our K is 8. So our vertex is 2, 8. Okay, which would be that point right there. And what that tells us is that the maximum height of the ball is 8 feet. Okay, and we also know that that happened 2 feet away from where Mia tossed it. Okay, so vertex form gives us the vertex, which helps us know where that highest point is. Okay, we also know that since A is -0.5, it will open downwards, which we can also tell obviously from the graph, but in case we didn't have the picture, we can know from the equation. Okay, but now we need to change that into standard form. So, okay, I'm going to write down -0.5 x minus 2 squared plus 8. And we are going to change this into looking like ax squared plus bx plus c. So we need to do the exponent, okay, but we have to be careful. We're squaring a binomial. So we're still going to have this -0.5 on the outside. I'm going to put my polynomial expression on the inside here of the parentheses still. And remember, this pattern is square the first piece, so x squared. At the end, we're going to square the second piece, so +4. And in the middle, it's 2 times the first piece times the second piece. So that would be -4x. Okay, and we still have our +8. Now we need to distribute that to everything. So you have -0.5x squared. This is like half of 4, and a negative times a negative, that would be a +2x. And then another half times 4 is 2. This time it will be negative. And our last step is combine those like terms together. So I guess I should say f of x is -0.5x squared plus 2x plus 6. Okay. And what standard form tells us, it's probably most important piece of information it tells us, is that the c is 6, which means the y-intercept is 6. And in terms of this equation, in terms of this scenario, that's where Mia throws the ball from. So Mia threw the ball from a height of 6 feet. Okay. I do want to point out that as this ball continued down, wherever it landed, I don't quite know. We will figure that out eventually in chapter 9. But it's not going to make sense to continue drawing our parabola because that would then mean the ball is going underground. So keep in mind that based on the scenario, based on real life situations, we might only have pieces of a parabola that model the scenario. So notice here it doesn't go into negatives because she's not throwing it from a negative spot. So we have our parabola, but it starts at the y-axis, and wherever it is, I can't quite tell you where right now, but it would stop at the x-axis because it's not going to go below ground. And then just to give you a heads up on the last page of your notes, okay, I'm not really going to go through it, but these are just the general things from this lesson. We have the algebraic way of saying things, although it does get a little weird towards the bottom there. But they do also give you some numbers to help you figure out number-wise what's going on here. Okay, as always, if you're having any questions, please make sure you're reaching out. Don't let things build up too much, getting behind. Make sure you're addressing any issues as we go.